Okay, we'll take a little bit of a more careful look at this character pi0, which was our first functor. Okay, what we'll see now is all completely elementary, and you would all have seen many ways of doing it, but the particular way is going to set us up for what we want to do later. Okay, so for a space x, we define pi0 of x to be the set of path components. Okay, so that is to say pi0 of x is going to be x divided by an equivalence relation, where I have to define the equivalence relation. Okay, so we define this equivalence relation, and what we'll do is, rather than simply defining the existence of a path, we'll look at all paths. So let's say our space is going to be a torus and a sphere, and I have a point P here and a point Q here, and I have a point R here. Then given P and Q, I have lots of paths between them, and I look at the set of these paths. But given P and R, there are no paths at all. Okay, so that tells you how we can define tilde. Okay, so we can define tilde in terms of whether the path is empty or not. Okay, that is in other words, we see that two points are equivalent if and only if equivalent in the sense of being in the same path component, if and only if the space of paths between them is non-empty. Okay, so you can think of paths as witnesses that these two are connected or not. And of course we need our main theorem here, which is saying that this is an. So we say that this tilde is an equivalence relation. Now how do we know this? We have to show that it's reflexive, symmetric, and transitive. And so let's look at it in terms of our spaces. So this is omega of x pp, and I have to show this is not empty. Well, this is because we can define EP in this, pp, and EP is given by EP of S is P for all S in 0, 1. Okay, so you take a constant path which just stays at P. So this is the first point, that it is reflexive. So it's a kind of effective way of showing reflexivity. How about symmetry? Symmetry is even nicer. So suppose we have P is equivalent to Q. This implies that, of course, omega of x PQ is non-empty. Okay, and then we define a function from omega of x PQ to omega of x QP. So if the first set is non-empty, so is the second set. Okay, so this is the function which will map alpha to alpha bar, where alpha bar of S is alpha of 1 minus S. Okay, and finally we have transitivity. So what does transitivity say? So transitivity is the statement, of course, that so P is equivalent to Q and Q is equivalent to R. So this will tell you of omega of x PQ is non-empty, as is omega of x QR. And it's perhaps time for a picture. So here we have P and Q. Suppose, well, I'll call this R prime now, it's no longer R. Suppose R was here and I had a path from P to Q. Then of course the path, and if this path was alpha and this path was beta, then the path is alpha followed by beta. But remember, we are parameterizing by 0, 1, so we have to go double speed. Okay, so for this, what we use is we use a map from omega of x PQ and omega of x QR to omega of x PR. Okay, and this is going to send alpha and beta to alpha star beta. And what is alpha star beta?